Welcome to the absolute pinnacle of modern marine engineering. At an unprecedented construction cost of $2 trillion, this is not merely a conceptual structure. It is an entirely new, sovereign artificial landmass. We are analyzing a modular floating megacomplex spanning exactly 50 square kilometers. To put this into an industrial perspective, the total displacement of this facility exceeds 100 million metric tons, dwarfing the largest supercarriers ever built by a factor of 1,000. The central engineering challenge of this megaproject is monumental. How do you construct and stabilize a massive, rigid platform in the most volatile kinetic environment on the planet? And how do you prevent the relentless forces of the deep ocean from tearing it apart? The foundation of this deep-sea infrastructure requires a complete recalculation of standard hydrodynamic principles. This floating continent is continuously subjected to extreme physical variables. The primary destructive force is structural shear stress, generated by deep ocean currents colliding with the massive submerged substructure. We are dealing with millions of tons of lateral force, combined with aggressive wave kinematics at the surface. Furthermore, the structural footprint must endure severe thermodynamic variations. The temperature differential between the sun-baked upper decks and the freezing submerged hulls causes massive thermal expansion and contraction. This cyclic thermal stress, combined with the constant kinetic pounding of the waves, creates a phenomenon known as structural fatigue. If conventional marine-grade steel and standard reinforced concrete were deployed here, the relentless cyclic loading would generate microscopic fractures, inevitably leading to a catastrophic structural failure within a matter of months. To counteract these absolute physical limits, civil engineers had to pioneer an entirely new class of construction materials. The core foundational matrix of the platform is not standard concrete, but a highly engineered composite known as ultra-high performance concrete, reinforced with a dense carbon fiber lattice, commonly designated as UHPC-Carbon. This is where advanced materials science meets heavy industry. The UHPC-Carbon compound undergoes a specialized curing process under controlled atmospheric pressure, resulting in an incredibly dense microstructure with virtually zero porosity. This absolute density prevents saltwater intrusion at a molecular level. More importantly, it achieves a compressive strength exceeding 250 megapascals. The embedded carbon fiber matrix acts as an internal shock absorber, distributing the kinetic energy of the waves across the entire module and completely neutralizing the risk of micro-cracking under severe bending moments. It provides the tensile flexibility of steel, combined with the compressive invulnerability of solid rock. However, the structural integrity of the concrete is only the first line of defense. The outermost layer of the substructure, specifically the areas directly exposed to the highest rates of galvanic corrosion, requires an armor capable of surviving decades in highly oxygenated saltwater without degradation. Engineers implemented a specialized protective cladding utilizing a high-grade titanium-aluminium alloy. This bimetallic shield is an engineering marvel in its own right. Titanium offers exceptional strength-to-weight ratios and unparalleled corrosion resistance, while the precise addition of aluminium creates a self-healing oxide layer when exposed to the elements. If the surface is scratched or impacted by marine debris, the alloy instantly reacts with the surrounding oxygen to form a microscopic, impenetrable barrier, permanently halting the electrochemical degradation process. The application of this titanium-aluminium armor to the UHPC-Carbon core involves a complex metallurgical bonding sequence. Massive, prefabricated alloy plates, each weighing over 50 metric tons and measuring precisely 10 meters by 10 meters, are aligned using automated positioning gantries. The joining process utilizes advanced plasma arc welding conducted in localized vacuum environments to prevent atmospheric contamination of the weld pool. This exacting process ensures a seamless, monolithic metallic skin across the entire submerged surface of the mega-complex, with surface tolerances measured in millimeters. Before a single module is ever deployed, the supply chain logistics required to acquire these extreme materials must be perfectly synchronized. Producing millions of tons of UHPC-Carbon demands a global network of dedicated manufacturing plants, processing specialized silica fume, precisely graded quartz sand, and high-tensile carbon polymers. Concurrently, the raw titanium must be extracted, refined, and forged in high-pressure vacuum furnaces to eliminate any molecular impurities before being alloyed. This entire supply chain operates with zero margin for error. A single batch of substandard material could fundamentally compromise a vital load-bearing junction of the floating city. The financial allocation for this foundational phase alone accounts for nearly $800 billion of the total $2 trillion budget. Every square meter of this floating facility represents a calculated mathematical victory over hydrodynamics, material fatigue, and structural stress. With the material science locked down, the engineering focus shifts to the geometric architecture of the floating city. The foundation is not a single, solid mass, but an interlocking honeycomb matrix of colossal, prefabricated hexagonal modules. The hexagonal configuration was deliberately selected for its supreme geometric efficiency. It offers the highest ratio of internal volume to perimeter surface area, allowing for optimal load distribution across multiple axes of stress. Each individual module acts as an independent buoyancy vessel, measuring a staggering 50 meters in diameter and plunging 30 meters below the waterline. However, a static floating structure of this magnitude would inevitably tear itself apart under the chaotic oscillation of open ocean swells. The engineering solution is a highly sophisticated, active hydraulic ballast system integrated into the hollow core of every single hexagon. This is the mechanical heart of the floating city. Deep inside the concrete shell, networks of industrial-grade centrifugal pumps are coupled to massive seawater intake valves. These pumps operate on a closed-loop automated control system responding to a central gyroscopic sensor array that monitors the pitch, roll, and heave of the entire complex in real time. If a localized wave trough causes a sudden drop in buoyancy on the northern perimeter, the system instantaneously injects thousands of liters of pressurized seawater into the ballast tanks of the opposing southern modules. This rapid fluid transfer artificially alters the center of gravity, perfectly counteracting the wave's kinetic energy and maintaining a rigorous dynamic equilibrium. The surface of the city remains practically motionless regardless of the hydrodynamic chaos raging beneath it. Fabricating these behemoth modules requires an industrial infrastructure of unprecedented scale. Traditional shipbuilding dry docks are entirely inadequate for the sheer volume of production demanded. Instead, an entirely new coastal megafactory was constructed, featuring a linear assembly line stretching over 5 kilometers along the shoreline. This facility operates on a continuous, vertically integrated manufacturing paradigm. The core fabrication technique relies on automated slip-form concrete extrusion. Massive hydraulic steel formwork slowly inch upward at a precise rate of 25 millimeters per hour. As the formwork rises, automated overhead gantries pour a continuous stream of the UHPC-Carbon mixture into the molds. This continuous pouring process is critical. It entirely eliminates cold joints' weak structural points that form when fresh concrete is poured over a previously cured hardened layer. By maintaining a continuous pour 24 hours a day, the structural integrity of the monolith is flawlessly preserved. The logistics of feeding this continuous extrusion process are staggering. A dedicated fleet of autonomous heavy lift transport vehicles moves relentlessly between the raw material silos and the automated batching plants. The mixing process itself is heavily monitored. Thermal sensors track the hydration heat of the concrete. Because the walls of the hexagonal modules are exceptionally thick, the core temperature of the curing concrete can spike to dangerous levels, causing internal thermal cracking. To prevent this, the slip-form rigs are equipped with an internal network of cryogenic cooling pipes, circulating chilled water directly through the formwork to extract excess heat and ensure a uniform curing gradient throughout the massive walls. Through this highly synchronized production pipeline, the factory achieves an astonishing output velocity. The completion cycle for a single 50,000-ton module is compressed into a mere fraction of standard construction timelines, with a new unit rolling off the slipway every 72 hours. Yet producing massive concrete blocks is only half the battle. Connecting them in the open ocean requires a level of mechanical precision normally reserved for aerospace engineering. The interlocking nodes, the critical junction points where one hexagon docks with another, are reinforced with massive forged steel brackets. The machining and installation of these brackets are completely handled by an army of multi-axis robotic arms. Human welders simply cannot sustain the stamina or the micromillimeter accuracy required for these continuous deep penetration welds. The robotic welding stations employ an automated submerged arc welding process, operating under a continuous blanket of granular flux to prevent atmospheric contamination and thermal shock. Before the welding even begins, the high-strength steel plates are precision-heated using induction coils to optimize their metallurgical grain structure. The robotic articulators then lay down flawless weld beads across steel plates exceeding 100 millimeters in thickness. The engineering tolerances demanded here are ruthlessly strict. Despite the module measuring 50 meters across, the locking nodes must align with an allowed deviation of less than 0.1 millimeters. To guarantee this microscopic precision, continuous laser metrology scanners sweep the geometry of the steel brackets as they are welded, instantly adjusting the robotic arms to compensate for even the slightest thermal distortion. Following the robotic welding, the structural integrity of every single connection node is verified through rigorous non-destructive testing. Automated crawling robots equipped with phased array ultrasonic scanners map the internal structure of the weld seams in 3 dimensions. Any microscopic void, slag inclusion, or incomplete fusion triggers an immediate rejection protocol. This is heavy industrial manufacturing, executing with the precision of a Swiss watch, a mandatory prerequisite for the final, and most dangerous phase, deep ocean assembly. To safely transport a 50,000-ton, 50-meter-wide concrete hexagon across open ocean swells, the logistics fleet employs a highly specialized armada. This consists of heavy-lift semi-submersible vessels acting in tandem with ocean-going tugboats equipped with dynamic positioning Class 3 or DP3 systems. The DP3 infrastructure represents the pinnacle of automated maritime navigation. It utilizes a triple redundant network of satellite uplinks, acoustic seabed transponders, and highly sensitive laser gyro reference units. These sensors feed real-time environmental data into a centralized algorithmic processor, which instantly dictates the output of omnidirectional azimuth thrusters located on the transport hulls. This allows the heavy lift fleet to counteract multi-directional ocean currents and severe wind shear, holding the massive module at the exact offshore coordinate with an allowed deviation radius of less than 1 meter, regardless of the chaotic sea state surrounding it. Once perfectly positioned, the most perilous phase of construction commences, the deep water mating of the modules, aligning tens of thousands of tons of concrete and steel in a constantly shifting fluid environment is an extreme engineering challenge. The solution relies on a dual-stage, V-shaped hydraulic locking mechanism. As the DP3 vessels inch the modules together, massive primary steel alignment pins, each weighing over 10 tons and driven by industrial hydraulic rams, are deployed. These rams exert thousands of tons of linear compressive force, forcing the V-shaped male connectors into their corresponding female receptacles, absorbing the kinetic shock of the colliding masses. With the modules mechanically locked, the secondary sealing protocol is initiated by a swarm of autonomous remotely operated vehicles, or ROVs, operating deep below the surface. These ROVs are equipped with high-pressure injection nozzles that pump a specialized hyper-viscous marine epoxy directly into the microscopic gaps of the joint cavities. This specific polymer is engineered to cure exothermically upon contact with salt water. As the chemical reaction occurs, it actively displaces any residual moisture, expanding and hardening to form an impermeable, semi-flexible molecular bond. This critical flexibility allows the entire $2 trillion complex to articulate slightly under extreme wave action, preventing the catastrophic structural shearing that would shatter a perfectly rigid structure. Before the superstructure is populated and the logistics hub becomes fully operational, the structural matrix is subjected to rigorous, real-world kinetic stress testing. Engineers utilize massive, localized kinetic wave generators to artificially bombard the perimeter defense modules with calculated wave profiles. These simulations replicate the hydrodynamic impact of extreme events, featuring wave heights peaking at 30 meters. Every semi-flexible epoxy joint and every titanium-aluminium armor plate is continuously monitored by an embedded network of over 100,000 fiber optic strain gauges. These sensors measure the microstrain and material fatigue in real time. Simultaneously, computational fluid dynamics models simulate the aerodynamic drag of Category 17 hurricane force winds exceeding 300 km per hour, dictating the precise aerodynamic mitigation profiles required for the upper deck structures. Ultimately, this floating megacomplex is much more than a marvel of heavy construction. It is a fully autonomous, sovereign logistics engine. To break free from the supply chains of the mainland, the facility must generate its own infinite power supply. The engineering core of this independence is a massive ocean thermal energy conversion, or OTEC, facility built into the central modules. The system lowers titanium intake pipes nearly 1,000 meters into the abyss to draw up freezing, deep ocean water. By exploiting the extreme thermodynamic differential between the warm surface water and the freezing depths, the OTEC plant vaporizes a low boiling point working fluid, such as anhydrous ammonia. The resulting high-pressure vapor drives colossal turbine generators before being condensed and cycled back through the closed-loop system. Coupled with submerged kinetic wave energy converters integrated directly into the perimeter walls, the floating city generates a continuous, infinitely renewable baseline power supply measured in multiple gigawatts. This unprecedented fusion of automated manufacturing, marine logistics, and thermodynamic engineering proves that humanity can now fabricate a self-sustaining multi-trillion-dollar industrial continent entirely free from the physical limits of land. Subscribe to the channel to explore more engineering limits pushed to the absolute edge.